We're going to look today into tactical long-term planning, a little bit the objectives that we follow when we do a multi-year prioritization. What is the role of this prioritization, long-term tactical planning in the selection and budgeting process, and some key elements that we need to consider for this type of analysis. So the tactical and long-term investment planning are important because they are used by all the road agencies in their budget for preservation of the assets. They need this planning because planning is associated with budgeting. So you need to prepare the plan and then you do costing, and with that costing you can put down your budget for the next year, your budget for the next 5 years, your budget for the next 10 years. The quality of this planning and budgeting has an impact on the condition of the roads, the pavements. This is what matters in this class. So the strategic level is typically long-term, as we have explained before. Is 20, 30, 40 plus years. It depends on the type of asset. But for roads, you know, a road, the lifespan of a road is somewhere between 20 and 30, 35 years. The tactical level is when you zoom into the 4-year segment or 5-year segment, and you look at the different projects, road projects, reconstructions, overlays, and so on, that you have scheduled. Then this schedule is typically based in the type of analysis we will learn today. There are some projects that I call here additional activities. These projects are political projects that the government has signed a compromise, an agreement with other stakeholders and groups in the country, or that the government has requested some loans from international organizations. So you put those two together, and now you have the total number of projects, schemes that you have for the next 4 years. Now you have to go and you have to rearrange the order in a way that you prioritize which are more important and which ones should go first. How we do that, we will look at it later today. Let's imagine we have done that prioritization, that assortment, and now we look into 1 year. And this 1 year is called operational level. And this 1 year, you still have to go your month by month, and you need to allocate projects, the commencement date, across the year for different points on time. So you will say in January, we will start with the overlay of Route 1, Control Section 27. On February, we will do 2. We will do the Control Section 5 of Route 2 and the Control Section 11 of Route 3. And you continue like that. Then, once you are doing these projects, you have to monitor, make sure their completion is satisfactory, and what is the level of condition that the overlay or the reconstruction will accomplish, and you update your system. So the long-term planning is this process that we utilize to achieve the best use of the resources that we have for the maintenance and preservation and expansion of pavements. It considers long-term impacts of the projects. That is, if I do a reconstruction today, or if I do a crack sealing today, how many years of additional lifespan that's gonna give me? So this is the type of things that I ask you in the first midterm. The plan tries to maximize the return on the investment, so accomplish the most cost effective so that you can meet the goals. Goals of an agency are typically in the form of maximize the condition, the surface condition, maximize or increase the structural capacity across the network, reduce the smoothness, so that is reduce the amount of vertical movements or improve that, do it within a given budget. You will also try to accomplish other goals if you expand from pavement management to road management, such as those of environmental impacts, congestion, travel time, okay? The long-term investment planning is then something that we require to accomplish the budgeting. And the budgeting is done for annual programs of works. So we identify what are the current needs. So you will have something like this. You will have a list of your road segments. And so on. Now, you identify what are the needs. Remember, this is what we did last time when we look into the current level of condition that they had. So if you have, for instance, roughness in meters per kilometer, and we know the roughness of this is as follows. So if we have a matching, as we did before, where we know that this is, for instance, a Milan overlay, and this is, for instance, maybe it's still a Milan overlay, and this one is now a partial reconstruction. And this one is, for instance, just microsurfacing. This one as well. So we will identify what is that every treatment requires, every segment, okay? That is what I need, identify the needs current and future. But this is the need for 2020, or let's say 21. But I also need to identify the needs for 2022, because I don't know if I am going to do this on 2021 or not. And I need to identify the needs for every single year as I move on. If I do or I don't do the treatment. So this is what we did in the exercise a couple classes ago. Then we generate the optimal long-term infrastructure investment plan. This investment plan is what we will do in 2022, what we will do in 2023, what we will do in 2024, okay? Now, how we make these decisions, I have told you last time, but there are multiple approaches. Last time I told you how to do this from a worst first approach and from a prioritization approach. Once this is prepared, we approve, and then this will become the basis for my 2022 long-term investment plan, 2023, 2024, and so on and so forth. And it's going to be for the next 20, 30 years. This is the typical asset management. You have 5 beings. You have on the top the policy and strategic direction, where you define what is the standards you want to accomplish. So for instance, you will say something like this. Just a second, please. So we will have policies and standards. You will have corporate strategic goals. and you will have your monitoring performance targets. So for instance, your policy will be deliver a pavement network in adequate surface condition. Okay. So the corporate strategic goal will be accomplish RI good RI levels. The target will be RI across the network less or equal than 1.8. The second one will be deliver a structural adequate pavements that last at least 20 years. So the corporate strategic goal will be accomplished good structural number or deflection basin area structural capacity. And the target will be deflection basin area across the network. So this is average, right? And this one was average as well. Bigger or equal than 21. But you can be more specific, of course, for highways and motorways. dBA bigger than 18 for collectors. dBA bigger or equal than 16 for local streets. So you can be specific. And of course, you can expand this to include other things. So gas emissions from minimize gas emissions from pavement maintenance. And then your strategic goal will be, sorry, that will be the strategic goal actually. Deliver environmental stewardship for pavement maintenance. Minimize gas emissions. And then this one will be reduce or select reduce gas emissions from pavement maintenance to XXX level. Okay, we can say maybe 500 kilograms per 100 kilometers of road repairs. And you can add as many as you wish. So this is the policy and the strategic direction, okay? Then we have here the long-term investment planning. When you select your needs, generate the long investment plan, and for that plan, you have your costing estimation. Then that costing estimation will land here in the budget management, okay? So that is my top bin, that is my policy and strategic direction. I have another one that is the, that is the long-term investment plan. So I have my program. that is the program that we had before, right? So this is really your long-term investment planning. Ah, yes, I cannot have the same name. Sorry. Yes. The next one is the budget management. So for the budget management, you already know what is coming from this, right? So you will have costing for this. So you know that this one will be 50,000. You know that this one will be 75,000. You know that this one will be 150,000. You know that this one will be 35,000. You know this one will be 27,500 because you know the cost, of course. Okay, so that's your budgeting. Then you have, of course, in the core of this, you have your information management where you know what is your inventory, what is the condition data you collect this information, what is the traffic that every road has. Okay, so that is, and you know also what is the performance targets that you want to accomplish across the network, and you have all the information on the resources that you have and so on. And then in the delivery is the way in which you are gonna take care of handling all this. And then eventually you will arrive into your monitoring and feedback where you have already done the entire process and now you want to see how well you are accomplishing these targets. So you go back here and you want to know how well you are accomplishing this, how well you are accomplishing that, and so on. So you will have something like this. So you will have for 2021, for 2022, for 2023. So for 2021, you will see what is the average RI in the network. For 2022, what is the average RI on the network? For 2023, what is the average RI on the network? For 2024, what is the average RI on the network? For 2025, what is the average RI on the network? For 2026, okay, and so on. What is the DBA that you are accomplishing? What is the reduction in gas emissions that you're accomplishing? All of them. So this is how you go and you control and monitor. So at the end, you have, from the outcome of this investment plan, you have the works program. And this is a list and the optimal timing. So if you choose this here, it's because 2022 was the best timing. If you choose this here, it's because 2023 was the best timing. if you choose these two here, is because 2024 is the best timing for that. You can also have new assets coming in here. That is possible. And you will say yes when you schedule the initial construction. From that moment on, the asset will have a condition value, and the asset will start to deteriorate from that condition. Okay, so we're going to look into what is multi-year prioritization. This is the method we considered last time, and is always oriented into accomplishing an efficient and cost-effective way to allocate the actions, the interventions. So you will have your target level of service for the network, and then you will have the inventory of assets in your network, and then you will identify what is the condition of those assets, and then you will prioritize. This is what we did for 2 road segments last time. I think I can close it now. But if you remember, in this class, this is exactly what we accomplished when we look at those 2 road segments. And we look at them for, I think, 3 years only, but we will, in a real life, we will be looking at this for multiple years. So when we were doing this, 2021, 2022, 2023, and you will continue 2024, 25, 26, we were doing a multi-year prioritization, okay? And we were then selecting a specific timing based on the budget. If you remember, at the end of the day, we were arriving in this table where you have the multiple combinations, and we were looking into the combinations that were not inferior, and based on that, we were choosing some of them depending on the amount of budget that they will consume. And from there, you have to handle the design, but this is just a stage that we have not covered in this class. This will land now into pavement design, is when you go and send and ask for a detailed design, and then the project management where you will implement that design and follow up the contractor that is building that, and then you will control the performance of the asset. The performance of the asset, there's something called performance-based contracts. And that means that you will hire a company to come on a specific year, do a repair, rehabilitation, or preservation work on the pavements. And then the company will handle the maintenance for a period of time. You will typically, you assign that for 3, 4, 5 years. And you pay the contractor if the performance, that is, if the roughness, if the cracking, if the rutting, if the deflections remain within your target. So that's why it's important, this performance monitoring.
So Professor,
yes.
So in those contracts, it's basically, I mean, it's all contractors' responsibility to do the testing and you know, evaluation of the pavements and all that. That okay, this is IRI is going below the threshold, so we have to maintain this and all that. So government basically hands out the contract.
No.
And the contractors, they have to monitor the whole network and make decisions and stuff like what? How does it work?
Separate contractors.
Separate? Okay.
Separate contractors. You cannot have the contractor that is handling the maintenance assess his work. You have to have a separate contractor that will go and check the quality of the works delivered and what is the roughness, what is the cracking, and so on. And based on that, you will issue the payments. So the contract will say something like this. For this is highway number 20, if the roughness condition is less than 1.5 on any given year, then we give full payment. If it is between 1.5 and 1.8, we will penalize you with a 20% penalty. If it is between 1.8 and 2.0, we will penalize you with a 30%, and so on.
Okay.
Okay. Sometimes, depending on what you're handling, you can also get additional incentives. So you can say, if the RI is less than 1, we will give you 10% extra. So it's an incentive for contractors, but that's rare. It's typically based on full price if you are below 1.8, let's say. Otherwise, penalties as far as you are away from the target. Okay.
Okay, thank you.
So prioritization, ranking, and optimization. Ranking is the most simple. It's only 1 year and is the sorting of options in 1 year. Prioritization is the sorting of options, but in a multiple period of time, but with basic tools. The tools you use to prioritize are cost effectiveness, cost benefit, things like that. Very simple. We're going to look into one of them today. Optimization is when you prioritize in multiple years as well, but you use a sophisticated tool, which is a formal optimization, which could be a heuristic optimization or could be a linear programming optimization. These are more advanced things, so I'm not gonna explain in full details because typically you use a platform that do the optimization for you. You just define the different options and things you want. Ranking is the most simple. It's only for 1 year. It doesn't consider next year, only consider this one. And what does is matching the list of ranked projects with the amount of available budget. And the way you do it depends on the agency guidelines, the way they do business. It could be as bad as a worst first, as the one we did in the midterm, or it could be keep the good assets good before you build new ones. So it depends. We will see. We start with the current condition. We look at the treatments that are applicable for each row segment. We estimate the cost. We could apply a weight factor. This is optional. We deploy a ranking criteria, and then we match the list to the budget. So for instance, consider that. We have 6 segments. Yeah, 6 segments. And you see the condition. The condition is in PCI, just to make it simple. And this is the applicable treatment: minor preservation, preventive maintenance, major, minor, preventive maintenance. And that is the cost in millions. So 1 million, 500,000, 3, and so on. When you go and you do ranking, if they follow a worst first approach, they will simply go and tackle the worst condition, as I explained before. And they simply sort the list from worst to best, and then select up until the point that they have no more budget. So if the budget is 4 million, they can only do the first 2. If the budget is 6 million, they can do the first 3. There's a mismatch, as a matter of fact, between the line that is on the slide and the budget that is shown on the title, right? You do realize for that line, you will be looking into a budget of 6 million.
Yes.
If you want to use some weighting factor, you can consider the amount of traffic. You can consider if it moves public transportation. You can consider if it has cycle lanes. You can consider elements that you care for. Traffic is typically the most important one.
Or just the heavy traffic? Can we just?
Total ADT.
Totally.
Yeah, you could consider heavy traffic as well. Maybe it's an important way to move from the port to the city, the merchandise is arriving.
Okay.
So yeah, but in this example right now, it's just overall traffic. So let's imagine you move 500,000 cars a year on the first two, 1 million on the following three, and 1.5 million on the other one. So you can use that traffic to multiply the condition and then obtain a weighted factor in there. And then you can use your costing to give a ranking. Now, the limitations of the ranking is first, you don't see the long term. You are only looking at 1 year. So it's like if you suffer from myopia. The rate of deterioration of the assets is not considered. This is also related to the first bullet, that you don't consider the long term. So if one asset is today, look at this. Sorry, here. Imagine this. Imagine you have these assets, two of them. Pavements. So you have section 1A and you have section 2R. And this one is surface RI 1.8, or let's make it 1.9. And this one is 0.7. The deflection basin area is 30. The deflection basin area is 34. Let's make it a bit more critical, it's 26. The rate of decay, if we make it linear, will be plus 1.1 meters per kilometer per year. What? And this one will be plus 0.5 meters per kilometer per year. So now I ask you, which one do you repair first? Well, it depends, right? But this one is in bad condition. This one is in better condition. This one in bad condition is deteriorating fast.
Yes, so we have to repair the first one first.
Yes, it's a no-brainer. Now let's imagine this reverse. And this one is 34, and this one is 14 in deflection basin area. So now this one is deteriorating at 0.5, and this one is deteriorating at 1.1 meter per kilometer per year. This one is good. It's a good condition, but it's deteriorating fast. This one is a bad condition, but it's deteriorating slow. Maybe you have a bunch of other segments etc., that you can attend now. And if you attend this one, it's still in good condition. So there's no point on attending this in this year. But it's deteriorating fast. So you know that next year, 2021, this is going to be at 1.8, and 2022, this is going to be at 2.5, and 2023, this is going to be at 3.2, and 2024, that is if you don't do anything, right? It's at 3.9. No, more. Sorry, this is wrong actually. It's 1.1. So this is correct. Plus 1.1, it will be 2.9. Plus 1.1 will be 4.0. And this will be 5.1. And this one is going at 0.5, so this will be 2.3. This will be 2.8. This will be 3.3. This will be 3.8. If you arrive at this moment on time, if you have not repaired them, they are almost the same treatment will be applicable. Now the question comes, this one will deteriorate faster. This one will deteriorate slower. So you should concentrate on the one that is deteriorating faster if you are in this moment on time. If you put the money here, yes, you are gonna make this one go back to probably 1.1 or 0.9 or something like that. But this one will move from probably what is a mill and overlay into what is a reconstruction. So that is a problem. So you should not let this one go from a mill and overlay into a reconstruction. Because if that happened, the mill and overlay cost, let's say $50,000 per lane per kilometer, and the reconstruction cost $350,000 per lane per kilometer. So it's a big of a difference. Now the problem is that when you are looking into the ranking, you don't consider the rate of deterioration. So you cannot see that is happening, that is coming. And of course, you have no efficiencies whatsoever because you are only looking into a 1-year prioritization. The prioritization
Professor?
analysis, yes.
Professor?
Yes.
So, well, we are saying that rate of deterioration is not considered, but what is stopping us to consider rate of deterioration when we do the ranking? I mean, if I'm doing the ranking, I can just create another set of parameter, rate of deterioration, and then sort of start ranking maybe based on rate of deterioration and of course, I mean the PCI or IRI value, but like what is stopping us from not considering
A stubborn manager sitting in the pavement management agency
Okay.
does not want to consider that, and that is only asking you to look into the current condition and give you a ranking based on that only, and doesn't understand the technical aspects of this.
Okay.
Have you ever come across people like that? Don't answer. I know yes.
Plenty.
Excuse me, sir.
Yes.
Is it possible that an intervention changes the rate of decay?
Yes, it is.
Is it possible to predict that?
Yes. Because you can fix drainage problems that are affecting the rate of deterioration of the structure of a pavement. If you are doing partial reconstruction. Of course, if you are only doing crack sealing, the drainage problems will not be corrected. So it depends on the nature of the intervention that you're scheduling, whether or not they will affect the rate of deterioration. And remember, you have rate of deterioration for the surface and you have rate of deterioration for the structure itself.
Thanks.
Okay. But Professor, determining the rate of deterioration for the pavement, it's going to take years because, or no, you can guess it from the substructure and the material they used, or how? I mean, how you get that numbers? If you only have but because previously you said you have 2 years to plan at most because you don't have time, the mayor wants it to be done fast. How you can generalize that on the
ideal situation is you have before and after analysis where you look into the trends before you do any type of intervention. And then you look at what is the trends after the intervention. So you isolate all mill and overlays and you look at before and after. You apply mill and overlay to all segments on a similar amount of traffic and similar environmental circumstances. The other one is done for the other treatment, maybe crack sealing. The other one is done for reconstruction. The other one is done for overlay. The other one is done for microsurfacing and so on. So you look at before and after trends. This is the material I think we covered before in the class. I'm not sure if I show you the before and after.
Yeah, I know the trends, but I meant because you, for example, you have 2 segments that are new and you are comparing them. And you said this one is deteriorating by this rate and this one is deteriorating by this rate.
Look. is like in the midterm, where you know that a treatment was done at a given point on time. And then you look at what is the trend before that. So you know you have in 2011 something, you are reading condition every year for one of your assets. And you know the asset is coming at 1.8, let's say, or let's say it's ratting. Okay, so let's say in ratting you have 1.8 ratting, 2.5 ratting, 5.3 ratting, but that's too much, 3.8 ratting, 5.1 ratting, and so on. But you know at some point at this moment, you did a Milan overlay. So you know your ratting reduced now to 0.1 or almost nothing, maybe 0. And then you start looking at this trend after that. So you know it's 2016, 17, 18, 19. So then you do, this is called before.
Yeah.
And this is called after. So you take your before.
And you make a curve, and based on that curve, you prevent the you prevent the after one.
Yeah. Exactly. And you plot that, and then you plot the other one.
Yes, yes.
Okay.
Yeah.
That's why I said that this class will kind of wrap up everything we have seen before, but from a conceptual perspective. So the prioritization is the optimal preservation and rehabilitation strategies in the life of the road. And you take and do this for the entire network, of course. And you use some benefit cost ratios, some cost effectiveness. These are the basic tools. You obtain a prioritized list of projects across time for multiple years and the cost. And then you look at what is the funding needs and what is the budget that you have for every year or group of years if you are getting a loan. The difference between the multi-year prioritization or prioritization and ranking is that prioritization is done for multiple years while ranking is done for only 1 year. Prioritization looks into several feasible treatments that you can do in multiple points on time, while the ranking only look into what you can do in a specific year. So sorry guys, let me just find out where I put it. Ah, here. So you're looking into what you can do, right? The what you can do, this is 2021. If you don't do that at this point, this Milan overlay is gonna turn into a minor reconstruction. And this partial reconstruction is gonna turn in some moment on time into a full reconstruction. And this microsurfacing that you could do in 2021, maybe in 2022 is not anymore and it's a Milan overlay. And will continue to be Milan overlay for a few years. Maybe this one over here, microsurfacing, will turn into a Milan overlay, but the pavement is deteriorating so fast that it will only be available for 2 years, and then you have to do a partial reconstruction. So it depends on how fast the asset is deteriorating. Maybe this Milan overlay will turn into a partial reconstruction and will remain like that for a few years up until the moment that will be a full reconstruction here if you continue doing your years. Okay, hope you got the idea. So this is looking into multiple periods of time and what is the applicable treatment, and is looking in the effectiveness of the treatment at every point in time. I know I have not shown you what I mean by that effectiveness. We look into effectiveness in terms of lifespan extension. If you remember the transition probability matrix, and we count the jump on cells, and we said if it is moving from this cell back this many years will be this effectiveness. So the effectiveness we have done so far is this one. And we actually grayed out these cells over here. And we have counted for a specific one, how many do you see coming here? Okay, so we have done this. And we have said then if it is 1 year, 2, 3, 4 years, one segment, 5 years, one segment, 3 years, 6 years, 3 segments, 7 years, 2 segments. And then we have say, what is the proportion of this out of the total? Okay, so you remember this? This is what we did already. And then we obtain the average lifespan extension by making the summation of this. So we have said before that this specific type of intervention gives you 585 additional years. Okay, so that's the effectiveness of a specific treatment, but the effectiveness can be measured in other ways. So I will show you an alternative way today. And more factors can be used in the analysis, in the multi-year priority analysis, because you have that ability to compare and consider all the elements. And if you do a good job, this is close to a good optimization analysis. Not all the time, because it's very difficult when you have a large number of segments. So you will be identifying these investment strategies to maximize the total network benefits and minimize the network cost. And you are considering constraints being the most common, the budget. So the optimization, which is the third approach, is very similar. You look at the current condition, but you also look at the predicted condition in the future. And you do a budgeting for the present and for the future, for every point on time. And then you look at how can you optimize the overall cost and condition, maximizing condition and minimizing cost. And then you find out what is the best set of treatments. This is what we have done before here in the ranking, where we have looked into these combinations of alternative ways to handle a specific row segment, right? We have 2 row segments here, this one and this one. And we are looking into 16 different possibilities that we then narrow down to 1, 2, 3, 4, 5, 6 possibilities that will depend on budget. So that is the projects that will fit the strategy. The ones that fit the maximum benefit in terms of condition and within the budget that we have. The output of this is almost the same as the prioritization. It's exactly the same, except that the order might be slightly altered. So when you look into the actual pavement management file that Nojan was asking before, that has the entire list, you can handle that in 2 different ways. You can handle this as an optimization if you run an actual optimization, or you can handle it as a prioritization if you do it manually here. Okay, so if you remember, in this one, you have to come up with the yes or no for each of these. So if I say, oh, it's not enabled, but as I make my choices, this will adjust itself. So when you do this manually or following some cost-benefit analysis, then you are doing a prioritization. When you invoke a solver, this one over here doesn't really work, but there are solvers. Where is the solver here? There are solvers, no, it's not in this computer, but there are commercial solvers that you can select and define that this needs to be found out so that you can maximize the bottom here condition, and you establish this as a budget. When you do that, then you are approaching the problem as an optimization. So both approaches are acceptable for the final project. Probably for you guys, it's easier to do the prioritization than the optimization. So prioritization is more common than optimization because it's simpler and it's easy to implement, as you can see in a simple Excel spreadsheet. So we will prioritize first the strategic level, that's the first one. Then we bring it down to the tactical level, that's the second step. And then we bring it down to the operational level. We have talked about that. And the key elements that this has is you can forecast the future conditions. You can see here in this Excel that we have, as we allocate things, we actually have a forecast of what is the PCI condition. You can establish the same in RI, but you will have the forecast of how the condition of these assets will no, sorry, that's incorrect, this one. You will forecast how the condition of the network will move and how much it's gonna cost you. And then you can look into that in a graph here. So you can look at the graphs of how much money you are spending on a given year, and you can look at a graph of how the level of condition is fluctuating across time. So that is the forecast of those conditions. And the selection of treatments and timing of options is simply the output of this when you look into the actions here. When you look into the consolidated zeros and ones for a specific year. So everything that has a 1, you are doing the corresponding action on that specific year. So you are doing the preservation in each of every that you have a 1. For the second year, you are doing this package. Most of them are preservations. We have a reconstruction here. We have a major rehabilitation here, okay? And for the next year, it's gonna be the same story.
Hi, Prof. Just I want to ask a question, right? So for instance, this Excel sheet we are seeing is for one homogeneous group, right?
No.
Am I correct?
Group
Okay.
A, Group B.
Okay, but there are segments. Do you combine all the segments and optimize everything? For instance,
Yes.
you have, say, 5 homogeneous groups and you have about 1,000 segments. Are you going to combine everything and optimize?
It depends on the capabilities of your system. If you have a system that is capable of handling all the homogeneous groups and segments of 100 meters or 500 meters, you handle it that way. This one in Excel right now is limited to about 100 segments. So you will have to combine some homogeneous groups and pack together. This, for instance, you see is 39 kilometers. This is 51 kilometers, okay? So this is 15 kilometers. It's being packed in groups. This is length. No, this is condition. Where is the length? This is the size, sorry, this is the size.
Okay.
So you can, if you have to, you have to pack it through homogeneous groups. So you can break it down in a size such that you can accommodate up to 100. But this is because of the limitation of the software, limitation of this Excel spreadsheet, right?
Okay.
Ideally, you will have segments of 100 meters,
Yeah.
right?
Yeah.
Or 500 meters, not segments of 10 kilometers or 7 kilometers or 5 kilometers.
Then what are the commercially, like off-the-shelf available softwares to do, you know, this kind of optimization? Like Excel has some limited capacity, right?
Very limited.
So what are the other options?
Dayton Asset Management. Okay.
Okay. Okay.
VMAX. Ransom
Okay.
Analytics. Inframodex. I'm not sure they have a website. Yeah.
Okay.
Okay.
Thank you.
In our case or in our project, what's the way forward? If you have over 1,000, do we prioritize and optimize the prioritized sections? If you could advise.
You have 1,000 segments.
Yeah.
Of
And
what
we have
size?
about 5 homogeneous
Total
groups.
size.
The total size, I haven't really checked, but I think it should be about 3,000 kilometers.
3,000 kilometers.
Yeah.
You have to put it in segments of 30 kilometers and bring it here in Excel.
Okay. Okay. All right. Thank you.
Can I ask a question
Yes.
regarding those 0 and 1s will be generated randomly was by those tools that you mentioned before?
They will be generated either manually, randomly, or with an optimization software. So you can go and look for, I don't have time to download it now live, but you can go and request your 15-day trial. You fill out the information. It's gonna be an add-in in Excel. And once you get the add-in, immediately you schedule a meeting with me and I will tell you how to use it. It's very simple. In 30 minutes, I will tell you how to use it.
Thank you so much.
Okay. I can't remember where I was. I think I was here. So multi-year prioritization is the same process as the optimization we have shown before. Forecast of future conditions is something we have already covered and is based on the different type of indicators that we can use. So rating, cracking, RI, okay, DBA, and it's all about getting the performance curve. We have talked about performance curves before. We need to create groups of pavements. So I think everybody's clear on this now. You can use the traffic volume, you can use the pavement type, you can use the climatic information, you can use the functional classification. You have to select the viable treatments. So for every asset on every point on time, you have to see the level of distresses, cracking, and so on. You have to look at the type of pavement that it has, the traffic volume, the rate of deterioration, and you have to identify what is the most applicable treatment type that you have. For maintenance, if it is flexible, will be crack sealing and microsurfacing. For preservation, it will be mill and overlay. For minor rehab, major rehab will be overlays or partial reconstruction and then full reconstruction. But if it is a concrete pavement, for maintenance will be the sealing of the cracks. Preservation will be replacement of some dowels and resealing of cracks. Minor rehabilitation will be block repairs. Major rehabilitation is going to be the repair of some slabs, but not all of them. And reconstruction is reconstruction. You are ripping it apart and making a new one. Okay, so you have some of those there. In the strategies for treatments, you have to look into your multiple periods of time. And you have to also consider what constraints you have. Sometimes constraints come in the form of the capacity of the contractor that can deliver no more than a given amount of kilometers of a specific type of treatment, maybe sealing the cracks. You only have 2 contractors and the capacity of their machinery is limiting them to do per season, per year, a maximum of 500 kilometers, the first one, and 300 kilometers, the second one. Maybe the weather in Canada is a bit harsh. We cannot do hot mix asphalt overlays all year round. When it's very cold, that season of the year, you cannot deploy treatments. So you also have to consider those limitations when you are looking into that. So you are gonna come, sorry, I just wanna skip through here because this is the way I can illustrate. So you can have one single treatment type, which is I will be doing mill and overlay every 5 years, forever. Or you can have a multiple treatment strategy where you have mill and overlay for 2 years, for 2 times, sorry. So on year 5 and on year 10. And then you let it deteriorate a little further down. And instead of doing mill and overlay on year 15, which will have been the previous option, you will wait until year 20 and do an overlay. And then you will wait until year 30 and do a reconstruction. And then you get the idea. So that's what is called multiple and single treatment. To develop this, you need to know what are the trigger levels. So the trigger levels is what we covered last time when we were illustrating this. And we establish these rules. And we say when you have this amount of rutting, less than 3, and cracking less than that, you can do crack sealing. When rutting is from 3 to 13, you do microsurfacing. When rutting is more than 13, you cannot do microsurfacing anymore. Now you have to do mill and overlay, but cracking has to be less than 20. If rutting is more than 13 and cracking is more than 20, and the flexion basin area is more than 18, you can do partial reconstruction or overlay. If this is not the case, then you have to go for full reconstruction. So those are the rules and the trigger levels. The trigger levels is the values for cracking, rutting, deflection basin that are associated to the rules. The set of rules is what I just showed you now. But there's another one here. And there's another one here. And then you have to have a set of rules for asphalt pavements for whatever is available in terms of interventions. And you have to have the same for concrete pavements for whichever intervention is available. Based on that, you will then, at the end of the day, be selecting. This rule is when I do this type of treatment, minor rehabilitation. This trigger point is when I do a major rehabilitation. The trigger point is important because there is an approach in which we use the trigger point and this dashed line to get an area below the effectiveness, the jump, and the deterioration all the way until you get to the same point. So for instance, consider this movement that I have here. I am deteriorating and I arrive into this point over here. I arrive into this point right here. And at this moment, I know I can do a minor rehabilitation. Maybe that minor rehabilitation is a mill and overlay. That minor rehabilitation is going to get me up to this point over here. It's not full recovery, you see, but it gives me this increasing condition. This is pavement condition, to make it simple. It's gonna deteriorate again, and it's gonna arrive at the same point of the same trigger for minor rehabilitation this number of time after. The area below this curve can be used as benefit area. And the same is true for the other type of treatments. That's just an example. So I think we're clear on the trigger levels, right? And the rules. We spent an entire lecture looking into that. So I'm just gonna skip through this example. So this area that is above the trigger level is what we call benefit. But this area is purely based on condition. It's not considering the amount of vehicles, the traffic volume, or any other criteria. You can alter the area and you can multiply it by the amount of traffic. So you can do a benefit that is based on the area times the traffic. And by the way, remember, this area will be the area above the trigger level. So it will be this area over here. This area below you don't consider because it's below the trigger level. There's no benefit on doing this after you go below the trigger. As a matter of fact, you might land in the next trigger and it's gonna end up badly because you are gonna move into the full reconstruction eventually. I'm not really gonna cover the marginal cost effectiveness completely. I will show you an example to make sense out of it, but it's a basic approach that we use instead of the optimization or the prioritization that we did last time with the non-inferiority analysis and the combinations. So the approach goes by establishing the effectiveness of each type of treatment. So you have for every asset, you will identify the feasible treatments for every analysis period. And this is based on the projected condition and the trigger levels. So it is exactly what I have done here. You will have the identification in 2021 of what you can do, the identification in 2022, what you can do, 2023, 2024, and so on. So this is for every analysis period and the projected condition that you have and the trigger levels. Then you are going to calculate the effectiveness. To calculate the effectiveness, you have to look at the area below the graph. So it is really this area multiplied by the traffic. To calculate the cost, you just look at the length and the unitary cost. I believe in this case, we had some costing associated to this. See, you have some costing and you have some length. So you multiply the length by the costing and you establish a total cost. Then we're going to establish the effectiveness divided by the cost. And that's what we call cost effectiveness. So the effectiveness is the area below the graph multiplied by the traffic, and the cost is just the cost. And then we select the treatment or the intervention that has the highest value for the first year. After that moment on time, there is an approach where you can do marginal cost effectiveness for the other strategies that you have. Because for a given section, you can do mill and overlay. Maybe that's the most applicable. You can do partial reconstruction and you can do full reconstruction, but it might be a waste of money if you do so. So I'm not really gonna elaborate here because this will complicate things. So I'm just gonna concentrate in establishing the cost effectiveness ratio. So consider this. Consider we have road segment A, and we have 4 possible interventions. A sealed coat, this is the effectiveness, 1, and this is the cost, 1. A 1-inch overlay, effectiveness 5, cost 2. If you wish, you could replace the effectiveness for the lifespan extension, if you knew. A 2-inch overlay and a 4-inch overlay. So when you do effectiveness over cost, your effectiveness is looking already into the lifespan extension. If you notice, it is this distance over here. This is your lifespan extension, but it's multiplying by the jump in condition that you observe, and then considering the area. So you have one axis, extension of life, another axle is the jumping condition, and you can multiply by traffic. So if you know this, this is fine. If you know just the life extension, well, that's what you use.
So in a way, it's like benefit cost ratio method in a way, right?
Yeah, exactly. Exactly. You will look into all the cost effectiveness, 1, 2.5, 2, 1.4, and this is for one row segment, segment A, alone. Now, if you are doing segment A because you absolutely need to do segment A, then of course you're going to choose this one because it has the highest value. You have also a segment B with 3 options. Your segment B, the highest option will be the first one because it gives you a cost effectiveness or benefit cost of 2. Your last segment, segment C, you have a value of 3, 1.2, and 1. So you do the first one. That's the most cost effective. And out of all these segments, assuming this is my total road network, which is a very simplistic assumption, I know, but assume this is the entire road network. Well, this 3 is the highest out of the entire network. So for sure, we will be doing this 3. Of course, we need to look at how much it costs and how much budget do I have. If I have 12 million budget and the cost of this one is 1 million, I still have 11 million left. So I can do it. The problem will be that the cost of this were 15 million, so I cannot do it. In that case, I could break this in 2 segments so that I can do it, or skip the segment until the next year, taking the risk that this segment might decay so much that the joint seal is not applicable anymore. That's why we need to look at multiple points on time. So let us assume I do this segment on the first year. I still have budget, so I can still go and choose another segment. The next segment to choose will be this one, because this segment is the second best in terms of cost effectiveness. It's a 2.5. Then I can move into my third segment. Now my third segment is a 3, as alternative 3 2-inch overlay for segment A, or alternative 1 for segment B. They both have the same cost effectiveness. So I cannot really tell which is best. You will have to look at the following points on time to see which one is deteriorating faster, and then address that one first. So after a while, you'll be able to identify which ones you are doing and look at multiple points on time, how the values of this is moving across time. So maybe after a given point, this treatment is not applicable anymore, and now the value of doing this treatment reduces and shrinks and drops. So there are this type of methods in the textbooks where you can do what I just showed you, the cost benefit, or you can do the dominance analysis and the branches that you have seen before. These are ways that people use to attempt to avoid doing the optimization itself. So these tools are important and are easy to use. and is assisting you to look at the life cycle of the asset and trying to identify when you do things and compare options, compare alternatives. You need to use the technical aspects to identify these treatments, these interventions, and to identify the cost. You need to use your engineering abilities. We need also to bring in this table the present worth method, because if you are doing something 5 years down the road or 10 years in the future, you need to discount that cost when you are looking at that cost from a budgeting perspective today. I am not going to step into this because you have covered this probably before in building economics, project management, cost estimation, or classes like that, or financial mathematics. But it's important, you need to remember that when you are putting something in the future, you should be discounting this in certain way. There's another one that is called incremental benefit cost analysis. So there are all these type of methods out there. I am running short in time, so I'm gonna just see if there's anything else I really need to mention here, because I need to jump into the next lecture. No, there's nothing really important here. Yeah. So I need to jump into the next lecture. And I need to talk about how can we expand what we have learned so far, and we can incorporate environmental impacts. But these environmental impacts could come in two ways. One way is when you are doing the maintenance and rehabilitation. So how many gas emissions are emitted by a mill and overlay? How many gas emissions are emitted by a reconstruction and so on? The other environmental impact is the amount of traffic that use the road. We are not worrying about that one. This lecture I gave in China, so that's why you have the title there like that. So we're gonna have a quick introduction here, but I'm gonna concentrate more in the methodology and case study and the results that we obtain. So this is done in the same process we have seen so far of maintaining, upgrading, and operating the assets, and looking at the long term. So we're still looking at the strategic horizon, and we're still allocating resources as we learned before. And we are, in this case, using an optimization approach to get the results. So what we're targeting is the fact that we don't have environmental considerations of maintenance and rehabilitation in the pavement management system. So we do select the treatments. We do consider the cost of each treatment and the life extension, the benefit. This is what we have seen so far in this lecture we covered before. But we do not consider the energy use and the gas emissions. So this is the part we're going to try to add now with this case study. So we're going to incorporate this in the pavement management. And for that, we will use a three-step approach. The three-step approach is going to extend the traditional formulation that we have, where we have some objectives and some constraints. What is this formulation? Let's look at it. We try to maximize the quality of the network. This Q is pavement condition index, or is international roughness index. So if it is pavement condition, you maximize it. If it is international roughness, you minimize it. If it is cracking, you minimize it. If it is rutting, you minimize it. If it is a structural number, you maximize. If it is deflection basin area, capacity of the pavement, the strength, you maximize it. You look at every segment, I, from the first one to the last one, segment N. So this is the entire network. And you look at every point on time, T equals 1 to T. And for it, you look at every segment length multiplied by the quality, the RI, the cracking of that segment on a specific point on time T. And so you have the first segment in 70 PCI on year 1, and you multiply by the 2 kilometers. So it's 70 by 2 kilometers, 140 plus. The second segment is 3 kilometers, multiplied by 60, 3 by 60, 180, 150 plus 180, plus you go for the next segment, segment 3, and so on and so forth. You have to constrain this with a budget, which is your annual budget. So for every treatment, J, that you apply on time T to a given segment I, you multiply the unitary cost of the treatment, 50,000 for mill and overlay, 3,000 for crack sealing, 200,000 for minor reconstruction, 350, 400,000 for full reconstruction. Okay, so you multiply that because that is per lane per kilometer. You multiply it by the length of the segment and by the decision, yes or no, if you are doing it on a specific point on time, a specific intervention. And that has to be less or equal than the budget. The yes or no is 0 or 1. But if you wish, you can do it continuous between 0 and 1 so that you can break a specific segment in a proportion. The modify approach in the first step is looking, if you see, I'm taking the constraint, cost times yes or no times length, and I'm turning that into an objective, and I'm minimizing the total cost. This triple summation here is the minimization of total cost for the entire network, for all applicable treatments that I will allocate. Plus, and I'm adding vehicle operating cost. So vehicle operating cost is something we have not talked about it yet, but it's just a way for you to estimate what is the amount of gasoline, oil, tire repairs, and maintenance that the vehicles will require. And people have developed equations that associate vehicle operating cost with the roughness level of the road. So I will leave that to you guys. You can go and look for them. You just talk the RI, goes into an equation and gives you vehicle operating cost. And look at the subject, the constraint. Look at my previous objective. It was the length times the quality. Quality, RI, quality, PCI, quality cracking, quality rutting, quality deflection basin area, okay? Right here is an objective, but in my modified formulation is a constraint. I am constraining on time T as dependent on time T minus 1. So I'm saying this year depends on the previous year. And it has to be bigger or equal than the previous year. So my condition has to improve across time or remain the same as the previous year. So the second step is my typical formulation where I have budget from step 1. So from this one, I will minimize cost, and this is gonna estimate how much cost I need to accomplish and sustain the current level of condition across the network. I will identify the budget out of this. To identify the budget, I can now move into this second step where I use the previous formulation. So step 1 allows me to identify budget. And I can put this value here. Why? Because I just get the average cost across time for every year. And I can try to maximize the network. And step 3 is an extension where I have the gas emissions G, yes or no, I do the treatment, and the length in kilometers. So this is 50 kilograms of CO2 equivalent for a mill and overlay per kilometer per lane. So when I multiply by 2 kilometers, the 50 turn out to be 100 kilograms for the 2 kilometers for the mill and overlay. And the X is yes or no. And it's based on your decisions. Remember, you have decisions here where you will say yes or no. So that is the X. This is my X. And the E is the same is energy. Energy consumed by the machine. Why? Because the energy consumed by the machine is related to the fuel that the machine requires. Gasoline or diesel or petrol. And that also has an environmental impact. So you can balance this with some weights, alpha and beta.
Sure.
Yes.
So that energy consumed is directly related to greenhouse gas emissions, right? I mean, the burning the hydrocarbon. So, I mean, like, why are we having two variables here? Because greenhouse gas emissions will be, I mean, they will be emitted from the engines who are using gasoline or petrol or diesel, right?
Yeah.
So why do we have energy consumption, fuel consumption as separate, and then greenhouse gases as separate?
Yeah, you can have only one if you wish. Sometimes you only have the gas emissions characterization, or sometimes you only have the energy. So you use whichever you have.
Okay.
So at this step, we already have budget from step 1. We have the level of condition we can attain from step 2. And what we do, if you look at my constraint, subject 2 is subject to the budget, right? So this is a constraint, and is subject to the condition that I identify on step 2. So I will still accomplish the same I typically accomplish without gas emissions considerations and within the budget. But now the system is going to select very carefully based on the environmental impact of the alternative. So we took this, and I'm going to show you a case study. This is probably your case as well when you are presenting your final paper. So this is a good example for you how to present it. In this particular case, we took 1,293 road segments, about 3,000 kilometers from Alberta. With those characteristics you can see there. And we look at the amount of energy usage and gas emissions from this paper, Chehovitz and Galehouse from 2010. They characterize how much gas emissions and energy usage will be utilized by a reconstruction, a major rehabilitation, a hard-in-place recycle, a chip seal, and a microsurfacing. So you can see here gas emissions in this column, kilogram per square meter, and energy use in megajoules per square meter. Okay? You also have the life extension, which you typically characterize. And you have the cost. And you have when you apply that in terms of roughness. Here are the details of what we're considering a reconstruction, what we're considering a major rehabilitation, what is a hide-in-place recycle, what is a chip seal, and what is a microsurfacing. And based on this characterization of binder, emulsions, aggregates, thickness, is that we can estimate this energy and gas emissions that we have here. Okay, so this column energy, this column gas, and this column details is added to what we typically have. So, summary of what we're going to do, we're going to look at a scenario A. A scenario A is minimization of costs with non-increase in roughness and an annual budget of 30 million. A scenario B is maximization of condition with an annual budget of 30 millions. And the outcome of this will be the optimal set of treatments and that are also respecting the network mean RI that I established before. And the last one will consider the energy usage. So the scenario preferred is C. The traditional scenario is B. So this is a scenario B. Scenario B, remember, 30 million. Don't worry about the environment. Nothing is going to happen. And let's only maximize roughness. So that's the scenario B. And this is the allocation. Remember, this allocation is coming from your zeros and ones that then get processed into a graph that gives you cost, or that you can balance the graph to obtain out of here what preservations you have, what reconstructions you have, what major rehabs you have, minor rehabs you have, okay? So you put them all together and you obtain this summation of what you're doing. In this case, is in 1,000 meters of surface. Of course, it fluctuates because the reconstruction is more expensive and consume more resources, so you can do less. While in other cases, you have less reconstruction and you do more of a cheaper treatment and you can do more. And nevertheless, this is no environment issues, scenario B. And scenario C, which is we worry about the environment, is reshuffling things around in terms of treatments and keeping the same budget, keeping the same condition, but trying to choose the treatments that give less impact. So compare B with C. Do you see that gray bar is called microsurfacing? And it's happening on year 2008, 11, 12, 13, 14. It's happening almost every year, this microsurfacing, okay? Here, microsurfacing was happening after year 2020, but you didn't have as much microsurfacing. The other thing you probably notice is these black portions over here. They are hard in place recycled. This is not the environment, I don't care about it. Look, they're almost gone. I'm talking about the black segments, the hard in place recycled. So hard in place recycled goes down.
Is hard in place recycle minor intervention or medium to minor treatment, or what is it?
It's like a mill and overlay.
Mill and overlay, okay.
Roughly, but you have a machine that comes and has a cylinder with tooth. The cylinder is a mill, but it is attached behind a paver mixer where you take and you rescue the aggregates. When you are ripping with the cylinder, you put it in this second part of the machine, mixed with binder. And after mixing, you place it right away on site.
Okay.
But it has a higher impact. See, 1 in terms of gas emissions, while the microsurfacing has 0.10, 10 times less. And in energy, use 13, while the microsurfacing use 2.2. So that explains the fact that from no environment consideration, scenario B, to environment consideration, scenario C, you drop the hard in place and you increase the microsurfacing. And there's also a little drop in the major rehabilitation, but it's less noticeable. How does this look like in terms of performance? Remember, when I was talking before, I told you we established policies, goals, and targets. Policy delivered X network, accomplished good level of RI, and our RI has to be less than a given value. How that transfers here? The mean network RI is, let's say the target is 1.41 maybe. My scenario B is accomplishing that. It was designed to accomplish that. My scenario C is also accomplishing, but it's not giving the same values. It is slightly above, but still within the trigger, within the target that you have from your corporate strategic goals and your target. So you are still accomplishing that. Now, in terms of gas emissions, maybe your goal is to reduce gas emissions. So let's see what is happening. A scenario B, I don't care about the environment, is the solid black line. A scenario C is the dashed line. A scenario B is showing total energy on the left and gas emissions on the right. Higher than a scenario C, I care about the environment, which is the dashed line. You can see that for most periods of time is below a scenario C. Overall, a scenario C has a 19% less energy use and a 24% less gas emissions. So this ties back to your policy of delivering environmental stewardship for pavement management, your corporate goal of minimizing gas emissions, and your target of reducing gas emissions. In this case, we could write it slightly different, by 10% within 5 years or something like that. So this is how you go and you implement this type of targets. We can run some sensitivity analysis to see what happens if I put more budget, what happens if I put less budget. I'm just gonna skip that. I'm not gonna worry about that one.
Are municipalities considering environmental constraints at the moment?
No,
So
not that I'm aware.
okay, so the analysis that you showed us in the case study, I'm assuming the Excel sheet with that solver tool, that would, the one on the right hand side, yeah, this one. So this would have another dimension to it, basically the environmental constraints, and then based on that, right?
Yeah,
Because we have to minimize the gas emissions and or energy consumption, right? So is
exactly.
does that make sense?
Yeah, you can add it. So I show
Okay.
you. I show you. I'm gonna let you guys do it, but I will show you roughly here. So yeah, continue. So you will add, you see how you have PCI, in your case called BRI.
Yeah.
You have the operational window treatment value. After you treat it, what is the value you gain? If you do nothing, to what value is dropping? If you do nothing, cost 0. If you do something, it costs money. We can have gas emissions. And in your gas emissions, you can say if this is equals to preservation, then you are going to take from the table of microsurfacing the gas emissions, which is 0.10 kilogram per square meter. So you're going to take 0.10 times the length, the size you will have to make it square meters or corresponding to the units you are using for the 0.10, right?
Okay. Yeah.
If not, look to see if that is equals to reconstruction, and you got the idea, right?
Yeah, exactly.
You just attach it there. It's very easy. Okay, gonna stop the recording now.